My name is Tsahi Zidenberg. I am a tech lead in Offchain Labs. I work in the Nitro team. And today we're going to talk about one-step proofs in Arbitrum. For me, this is the most basic explanation of how Arbitrum, or most optimistic rollup, actually works and what makes it correct. We'll start with a toy simple problem. Let's say I want to do this computation. I want to do a factorial of a not small number modulo another modulo a non-small prime. And this is just a toy problem, of course, but for me as a programmer, it's quite an easy problem to solve, right? All I do is I write some code. In this case, I write it in Go. I compile this code. When you compile the code, it compiles to an assembly. This was done on an ARM64 machine, so this is an ARM64 assembly. And I execute this on my laptop. Specifically, this will take more than a second, less than a minute to execute. And in the end, I will have a result. Not only will I have a result, but any one of you that will execute this code will have the same result. And that's all fine and good. But how do I prove this result on chain? How do I prove to Ethereum that this is indeed the correct result? So the first simple in a quotes approach would be, well, to prove it on chain, what I need to do is execute it on chain, right? So instead of Go code, I will write Solidity code. This is already a little bit problematic because Solidity has a few constraints. You can't do a few things are harder there. And I will compile it to EVM. EVM is the assembly used on Ethereum. And then I will execute it on chain. This is a major problem because executing this one, I didn't go through the gas compute calculation, but I hope you trust me that it's very easy to define a problem that will take days and years of executing on taking the entire blockchain space. So sometimes I want to prove you the result, but I don't want to execute this computation on chain. So what do I do? What I do is a third approach, which is provable execution. So it will look like this. I will start with Go code. It is exactly the same, with some caveats, but basically exactly the same Go code that I used originally for my, when I executed it on my laptop. I will compile this Go code not to ARM64 or x86, but to WASM. WASM is WebAssembly. It is another type of assembly made to be emulated by software, originally WebAssembly because it was made to be emulated by browsers. And I will take this WebAssembly and I will execute it on a special emulated machine called Arbitrator. After I execute it on Arbitrator, all I do on chain is prove the execution on chain using the fact that I executed it on Arbitrator. And what that means is what we will go into depth right now. So what is Arbitrator? Arbitrator is written in Rust. It is a fully emulated machine, so a fully emulated virtual machine. It executes WASM. It is deterministic. It has hashable state, and it can produce one-step proofs. All of those we will talk about now. So the first thing I said is Arbitrator is fully emulated and deterministic. That means that if you look inside Arbitrator, if you look inside the code, what you will see in essence is exactly what you would expect to see of every fully emulated machine and even of every computer and every CPU. So the Arbitrator machine has representation for the code that is executing. It has representation for the memory, for the entire memory space that a program sees. It has a representation of stacks for the local and the WASM for local and the WASM stacks. And it has a program counter, which is a pointer that says what is the next instruction that I'm going to execute. And if you look in the code, in essence, the arbitrator does exactly what you expect of an emulated machine, which is it has basically a huge loop. This loop fetches the next instruction that needs to be executed. It loads it. It advances the program counter, which is the pointer that says what's the next instruction that needs to be executed. And after that, there is a huge select, or in Rust it's called match, which goes over what's the opcode, and according to the opcode, I will just do the thing that the opcode says. In this case, the code we have here is of the opcode I32EQZ. It's a WASM not. Pop the top of the stack. If it was a 0, push a 1. If it was not a 0, push a 0. And that's basically, when you compile your code, that's what all code compiles to. A sort of very, very simple instructions. What arbitrator has that's not true for most emulated machines is, first of all, we've said it is deterministic, which means there is no source of non-determinism. So mostly clock time, wall clock time has no meaning in arbitrator. Right? There is no place it can get data that is not fully deterministic. Another property it has is it is hashable, which means I can get a 32-byte hash that depends on every bit of state of the arbitrator machine. So the entire memory, all the code, all the stacks, the full machine that is currently emulated, if I can go and get a hash, one 32-byte hash that depends on every bit of state in the entire machine. So when I say arbitrator execution is provable, what I mean is this. Given a machine hash at some point, I can prove the next machine hash. So if we both agree, or if I have proved machine hash in step n, I can prove absolutely what will be machine hash in step n plus 1. Now, by extension, it means that if the first machine hash is known, so the initial machine state is known, the entire execution is provable, right? Because step after step, it is all provable. Now, this extension is not at all trivial, right? Proving billions of steps from proving one step is not at all trivial. It is a huge undertaking. This is what we call the BOLD protocol. I think it is an ingenious protocol. I love it. I recommend everyone to learn about it. But this is not our topic. Our topic is this. Given one machine hash, how can I prove the next one? And when I say prove, I absolutely mean prove it on chain, prove it on Ethereum, which means I have a smart contract. I have a smart contract that does this proving. Smart contract, I have here the link to like the code path in the Nitro repository for it. And it has an entry point which is called prove one step. Prove one step is a function. It receives two important inputs. There are other inputs, but we won't talk about them. The two important inputs it receives, first of all, what was the previous machine hash? What's the given that we're proving from? And second of all, it receives a large byte array that we call a proof. Its output, thanks to these two inputs, its output will be that next provable machine hash. So it will tell us the next machine hash, and if it agrees, then we have proven, basically, our claim. And to talk about how it works, I will first talk about arbitrator machine in Solidity. So we have the arbitrator machine in Rust, right? The local executed machine. This has the full state of everything. It might have hundreds of megabytes of state in memory. The Solidity implementation, of course, cannot have hundreds of megabytes of state. What it has is it has small state. It has state of a few functions. So it has the full program counter. It has, for example, it holds modules root. So it holds one hash which depends on all the modules, and all the modules hold all the code and memory and global variables. So all of that is condensed into one hash. The stack is interestingly condensed into the top few elements and a hash of all the rest. That's because stacks were not using Merkle tries, we're using Merkle stacks, if you will, that makes proving computing hash from this sort of thing simple. So the one-step, the proof that the one-step proof entry accepts, that large byte array, the first part of it will be the deserialized machine. So it will be code, it will be a byte array that Solidity deserializes into arbitrator machine, right? And the first thing, the almost first part in the one-step proof entry is I deserialize this machine, and then I go and I check what's the hash of this machine. If the hash of this machine matches the given hash, that means I have proven everything in this arbitrator state machine. So I have proven the top few elements of the stack, I have proven the program counter, and I have proven the module root. The next step, just like I have a representation of the full machine, I have some small representation of a module, the current module. And it will come, I will add into my proof the representation of this module and a Merkle proof. This Merkle proof proves that my module really is a part of that arbitrator machine that I have already proven. After that, in the same manner, I now prove a piece of the code. So I Merkle prove a piece of the code against the module which I Merkle proved against the arbitrator machine. And now I have proved what's the next instruction that has to be executed. So I have proved the right part of the code, I have proved the top few elements of the stack, and I have proved what's the program counter. The next step in the one-step proof looks very much like executing, looks very much like the execution of arbitrator. So it will do exactly what the local arbitrator machine does, which means at first it will advance the program counter. Then there is this large select, right? Check what's the opcode, match it against every possibility of legal opcode, choose what you're going to do, and then execute it. And here is execution, execute EQZ, which is the Solidity implementation of the same thing we saw on Rust. So I know that now I need to do an EQZ. And so pop the head of the stack, check if it's a 0 or a 1, push a 0 or a 1 accordingly. When I did both the when I did both the program counter advancement and that execute EQZ, I changed the representation of the arbitrator machine. I changed what I now know about the world. So all that's left for me to do is check the hash of this new updated machine. And this will absolutely 100% proven to be the next machine hash. So I have solved the problem I showed you at first. I proved that given one machine hash, I can prove what the next machine hash is going to be. By extension, using bold algorithm, I can prove, given the first machine hash, I can prove to you the entire execution of everything that can happen now. In Nitro, an execution, what it does is it produces a block knowing the previous block. So if we both agree, or if Ethereum believes that it now knows what's in block n, what's the hash of block n, and what's the next input, I can prove to Ethereum what's going to be exactly block n plus 1, the arbitrator, and that's how basically ARB1 is proven. There is then another step of extension, which says that given we divide the blocks into something called assertions. So every assertion proves a bunch of blocks, and that's all also done using bold. So because we can prove one block, we can also prove a bunch of blocks. Those are called assertions. And what you see on-chain in Arbitrum is you see on-chain assertions, and each assertion is proven by accepting that the previous one is correct, and we know all the rest of the input. Okay, so let's go over what exactly is that code. So I didn't have code samples here because it would be too difficult, and I'm doing something very much more hand-wavy. But this command replay main.go, we have the actual code that is the on-chain provable execution. So we said we are executing something over arbitrator and proving that. That's what we're executing over arbitrator in ARB1. So the algorithm goes like this. First of all, you need to read the previous block hash. Then you need to load the state of the block from that block hash. Then you need to load what the next transactions are, what is the next input. Then you execute those transactions, and some of those might be stylus transactions. Then you compute the next block hash, and you finish execution. 99.999% of those instructions of the WASM instructions executed are going to be just like the EQZ that we saw. They do very simple things that are entirely in WebAssembly, right? You write to memory, load from memory, push to stack, pop from stack, do some computation. But there are a few places where you need some communication with the outside world, where we have added WASM-like instructions. We call it WAVM, W-A-V-M instructions to assist the extra required functionality. So, for example, to get previous block hash and finish execution and compute block hash, we have something called a global state. Global state is basically the main input-output of the system. So, when I said the first machine hash is given, the first machine hash is one-to-one computable, knowing only the global state and the constant code, which doesn't change. So the first machine hash is known by just by global state. The last machine hash is only depends on global state, and that's how. So when my executable has an input of the previous block hash and an output of the next block hash, this is how that works. We have an interesting read inbox, so I can read the next transactions, what I need to do is read the inbox. The inbox is something that was posted on chain. My one-step prover knows what's posted on chain because it exists on the same chain. So it is very easy to prove to it what was proven, what exists on chain, and then I can read inbox from it. And my personal favorite, one of the latest additions to the WAVM is a link module. Link module allows you to add a new module to the same arbitrator machine, which means you can now load dynamically more code, which is exactly how stylus works. So when we allow proving WASM executed smart contract, this is what's going on under the hood. The interesting part, and when designing all of those, is to make sure each of them can be one-state provable. So for each of them, we have both an implementation that executes them and a solidity implementation that, if required, can prove them absolutely, can prove the next block hash from the previous one. At this state, I will say thank you. I'm Tsahi from Offchain Labs. Come find us at the Arbitrum booth in the full event that will start. And I am just on time. Thank you very much.